Hello and welcome to our tutorial series about line differential protection. Line differential protection is a core element of line protection and is applied from transmission down to distribution voltage levels. Our tutorial series should give you an introduction and deep insights into line differential protection theory and the CPOTEC 5 line protection devices. This session is about protection communication. We want to give you some insights about the possibilities that we offer in our CPOTEC 5 portfolio, and we have prepared a DIGSI 5 demo. If you already joined one of our last energy automation webinars, you already know the Q&A field on the upper right side in this application. Please enter your questions there. We will collect them and answer them live in a Q&A session for those who attended the tutorial series. My name is Nina Hühn, and I'm a technical expert for differential protection. I'm happy to do this session together with my dear colleague Philipp Stachel. Philipp, the stage is yours.
Thank you, Nina. I would also like to welcome you to our tutorial series. My name is Philipp Stachel, and I am the product manager for CPOTEC 5 line differential protection devices. In the first part of this tutorial series, we presented the basics of line differential protection. You learned that the reliable communication channel is required. In this session, we will focus on the available communication options for CPOTEC 5. Let's start with the agenda of the second part. The agenda looks as follows. First, I will give you some insights into the protection interfaces and the available communication converters. In the second part, I will present you the workflows for the advanced versus the classic protection interface. Nina will then present you 3 prepared demos in DIGSI 5, where she prepared a redundant communication, a multiplexed operation, and also a 4-ended ring topology. In the fourth part, I will give you some insights into the line differential protection over IP Ethernet networks. And Nina will end this with a demo in DIGSI 5 with a line differential over IP demonstration. Let's come to the protection interfaces. The CPOTEC 5 base module provides 2 slots for the communication modules. For the modular devices, the CB202 module can be added, which provides another 3 slots. In such a slot, you can plug a communication module. This is shown here. This is such a communication module where you have 2 fiber optic connections, 2 times ST connector, 820 nanometer. Or this could be another option where for a serial communication module with the USART for the long distance or the Ethernet BD module with 2 fiber optic using twice LC SFPs. For direct fiber optic connections, there are modules from up to 2 km for multimode, up to 100 km single mode. If 100 km are not enough for your application, you can use a fiber optic repeater, which further extends the distance up to 170 km, and this can be even cascaded. We will come to this later. There's also an option for pilot wire communication, where you use a communication converter, which you can use up to 20 km 2-wire copper twisted pair. And there are also options available where you can connect to multiplexers for wide area networks. Here we have interfaces for the IEEE C3794, which is an optical interface, or E1 or X21. The legacy technology is SDA technology, which is end of the lifetime. So today we're using communication over MPLS networks. And we will also have a look for this one later. And the latest option you have is the direct IP-based Ethernet connection for the line differential communication over Ethernet networks. We will give you a presentation for this also later. Let's have a look at the direct fiber optic modules and first start with some recap on fiber optics. In this slide here, you see on the right-hand side a diagram where you see the damping of a fiber optic, on a typical fiber optic. So the curve shows here that there are some maximum dampings which you can't operate, but you see also some minima at this location and this location here. So for these wavelengths, this is used for the fiber optic in practice. So it's optimized to use 1300 nanometer for long distances and also 1550 nanometer. This is a reason because of these quite low damping of the fiber optics. For the multimode is commonly used 820 nanometer, where you have a bigger diameter for the fiber optics. So there are 62.5 micrometer and also 50 micrometer core diameters available, which can be used for the CPROTEC 5 and also for the communication converters. This is used for access to multiplexers or for very short fiber optic applications. If you have to bridge longer distances, then you will use single mode fiber optics. As I said, using a single mode fiber optic which has only 9 micrometer diameter. Yeah, sometimes the confusion about 1300 nanometer or 1310 nanometer. This is due to the source of the light generation. So for the multimode fiber optic, often LEDs are used as a source, and then you speak about 1300 nanometer. Where for single mode fiber optic, a laser is used as a source, and then we speak about 1310 nanometer wavelength. Sometimes I got also the questions regarding the single mode LC connector polish. For the CPROTEC 5, we use a straight physical contact, also PC aberration, or PC type aberration. The angled physical contact, APC type, is often used in DWDM networks and not for CPROTEC 5. If a single fiber is used to transmit light of different wavelengths, we speak about wavelength division multiplexing, WDM. This technology provides a higher bandwidth over a single fiber optic and is therefore commonly used in wide area telecommunication networks. For the CPROTEC 5, fiber optic modules are available for both wavelengths on a single fiber, so-called normal WDM. SFPs for normal WDM are also available for fiber optic repeaters. This means that 1310 nanometer and 1550 nanometer are used on the same fiber optic. For telecommunication networks, coarse wavelength division multiplexing is available, providing 16 channels from the whole range from 1200 nanometer up to 1600 nanometer in 20 nanometer distances, and also WDM dense wavelength division multiplexing with typically 40 channels in a narrow range from 1300 nanometer up to 1565 nanometer. There are also special fiber optic applications available for the CPROTEC 4 devices, where you can have such a passive mix of 1310 nanometer and 1550 nanometer. So you can connect two devices and use a pair of fiber optics for transmission application. There's an application note for this particular one. Coming back to the CPROTEC 5 direct fiber optic modules, depending on the distance to be covered and the type of the fiber optic available, different types of multimode or single mode modules can be selected. The settings in DIGSI 5 are shown on the right-hand side. For direct fiber optic connections, we recommend to set the lowest appearing bitrate to 2 megabits per second. On the left-hand side, you see different options to be used for the modules to be plugged in the Cipotec 5 device. So we have options to cover up to 2 kilometer. And then we have also available options for wider ranges to be bridged by the fiber optic communication channel. In the DIGSI 5, you set, in this case, a direct fiber optic connection. The protection communication channel is continuously supervised. After the protection interface reconnection or the power up of the device checks the topology during a so-called handshake process. So it looks that the right partner are available. The right partners are detected by a configuration in DIGSI through the addresses of the device. So default setting is the device number 1 is 101, and device number 2 is 102. And you specify which device the actual device belongs to. Here in this case is it device number 1. So it's checked that the correct devices in the topology are available. Then also the number of received and sent telegrams are logged. There are thresholds in the DIGSI 5 when then these numbers of sending and receiving telegrams exceed, the errors exceed such level, then you will get an error in the logs. Also, the Cipotec 5 continuously measures the device time offset, which I presented in the first part of this tutorial series. And if there is something outside the range, if there are jumps or some asymmetry detected, you will also get an alarm. In case of redundant communication channels, the device selects the protection interface with the higher bandwidth setting. This is also depending on the lowest appearing bitrate. So this is the selection criteria. If you have a ring topology, there is a hot standby connection between the devices number 1 and number 2. And in case there is some failure in this ring, there is an automatic changeover from the ring to the chain topology. Sometimes you will find the stated maximum distance in our hardware manual is at the limit for your application. In this case, you can calculate the expected maximum distance based on the optical budget and check the usability, because we also made some assumptions for providing these numbers in our hardware manual. And you will find if it's okay for the application. Let's have a look in the example. Here in this example, you will also find in the hardware manual for a particular module, you will find the minimum optical power output of the module. In this case, here we have -5 dBm. And you see also the receiver maximum sensitivity. In this case, we have -34 dBm. The optical budget is the difference between both numbers. So the optical budget, OPB, is calculated by the difference. In this case, we get to 29 dB. This 29 dB is the optical budget which is used for the losses. The losses will occur on the fiber optic distance, but also for splices, joints, links. And here we give some numbers. So in fiber optic, damping coefficient is in dB per kilometer. For multi-mode, you will have the numbers here, and also for single-mode fiber optics. And also for the connections. So for single-mode splices, multi-mode connections, or single-mode connections. So assume that we have a 1310 nanometer single-mode fiber optic with 20 splices and 10 connections. Then you get the numbers from the table on the right-hand side. So we have 0.33 dB per kilometer for the fiber optic. The splice losses, so we have 20 splices. This means 1 dB losses for the splices. And for the connections, we have 10 connections. So this means 1.5 dB. And then it's recommended to add some safety margin to be on the safe side. So here we recommend to use 3 dB. So the maximum distance which you can bridge with this application is then the optical budget minus all the losses divided by the fiber optic losses per kilometer, and this gives you, in this example, 71 kilometer maximum distance. A commonly used protection interface found at multiplexers is defined by the IEEE C3794 standard. The standard describes an optical interface using n times 64 kilobits. N times 64 kilobits means that the communication channel is a setting for the multiplexer, and CPROTEC 5 supports a 1, 2, or 8 of such channels to be used. This is a setting which you will find in DIGSI 5 on the connection type. And consider some channel asymmetry for this type of application. For C3794, we recommend to set the parameter difference in sending and receiving time to 0.3 milliseconds, and in special applications up to 0.6 milliseconds. For IEEE C3794, you should consider that the end-to-end network communication delay depends on the used bit rate, so n times 64 kilobits. Also on the communication path between the relays, so the time of residence in all the communication nodes, the multiplexers or the MPLS routers. Also the propagation delay of all the communication links, so the fiber optics, the length of the fiber optics. And also the set speed of these communication links, if it's 1 gigabit per second or up to 10 gigabits per second. In case of circuit emulation, that means using SATOP or CSOPSN over MPLS, the time also depends on the ingress MPLS router, here particularly on the packet payload size, which needs to be packed into MPLS packets, which is usually configurable, and also on the egress MPLS router. Here it's particularly the jitter buffer size, which is also usable configurable. Let's come to the communication converters available. If the maximum distance to be covered is higher than 100 kilometers, you can use an optical repeater to further extend this reach. The fiber optic repeater with the order code shown here has several order options. The X stands for the different type of the SFPs. So the maximum distance to be covered are 24 kilometer, 60 kilometer, 100 kilometer, 170 kilometer. And there's also options for normal WDM. The fiber optic repeater multiplexes port 1 and port 2, which are the two fiber optic ports running at 820 nanometer, into port 3, which is SFP for the long distance fiber optic distance to bridge. We have a CPROTEC 5 device or CPROTEC 4 device, and you connect this to the fiber optic repeater using multimode fiber optic of up to 1.5 kilometer. And the fiber optic repeater then bridges a longer distance of up to 170 kilometer to the remote end. In the remote end, the fiber optic repeater decodes the data for the opposite CPROTEC 5 or CPROTEC 4 device using 820 nanometer multimode fiber optic connection. For very long distances, the fiber optic repeater can be even cascaded, as shown in the figure below. But this requires that there is a power supply in the middle of the two substations. So up to 3 times 170 kilometer can be realized in such an application. The multiplexer, the fiber optic repeater uses a transparent data transmission, so there's no framing, and up to 2 megabits per second data transfer. Another method to bridge large distances for line differential protection is the use of wide area telecommunication networks, shown here. To access such a network is provided through multiplexers, the edges. Electrical interfaces like X21 or G703.1 can be supported using the communication converter CCXG. You have the order code here, and it provides the synchronous and asynchronous communication. The interface X21 can be configured for 64 up to 512 kilobits per second. For the interface G703.1 is only 64 kilobits. It provides one port of multimode fiber optics for 820 nanometer, an interface for CPROTEC 4 and CPROTEC 5 devices. And the selection of the data interchange is controlled using a push button. There's also live contact to monitor the device, as common for all of these types of these communication converters. Also for E1 or T1 interfaces of multiplexers, a type of communication converter is available and shown in this slide. You have here the order code, and it provides a synchronous data transfer of 512 kilobits per second, which is used for the CPROTEC 5 and CPROTEC 4 series. There are also options available for asynchronous data transmission, which is not used for the CPROTEC series. It multiplexes two fiber optic ports into the E1 or T1 port. The E1 or T1 is available as a BNC or as a 5-pin. For the E1 is only the BNC connector. Line differential protection can also be transmitted using a pilot wire, which is a pair of twisted copper wires. There's also a need for a communication converter in this application. The order code you can see here. A pilot wire uses an SHDSL communication, and this can be up to 12 kilometer. You have also a possibility to cascade the pilot wire communication converter once, so you can bridge a 20 kilometer distance. The pilot wire is prone to some overvoltages, as can be seen in the next slide. So the pilot wire communication converter provides an isolation voltage of 5,000 volts. The setting of this communication converter is 128 kilobit per second, which is used for the CPROTEC 5 devices and CPROTEC 4 devices, but can be also configured using jumpers to 2 megabits per second. So CPROTEC 4 with the FO5 module can be connected, which is useful for the 7SD 52, 7SD 610, 7SA 52 and the 7SA 6 distance protection devices, and also for the CPROTEC 5 series with the USART AD 1FO or the USART AE 2FO modules, which can be used in the 7SD8, 7SA8, 7SL8, 7UT8, and also in the universal protection device, the 7SX8. Let's have a look at the pilot wire communication. And pilot wire communication is an electrical long-distance data transmission using SHDSL technology for the actual device, but in the past we also used type of ESDN communication. This is the older type of communication converter. So you need a pair of communication cables. So this is a telephone line or power, the pilot wire. So the maximum distance is 12 kilometer or 20 kilometer, but there's a high risk of induction voltages due to laid parallel power lines. And to overcome this risk of high voltages, there are additional isolation transformers available. It's shown in this slide here, and you can also find the order codes for 20 kV and also for 6 kV isolation voltage. The communication converter itself provides an isolation level of up to 5 kV. If the remote end relay is a CProtect 4 device, some consideration needs to be done, which are summarized in this slide here. In general, the CProtect 5 and the CProtect 4 line differential devices are compatible. But for retrofit applications, you have to consider some aspects. For example, if you want a direct connection of up to 2 km, or you can use the USART modules directly with the FO5 module in the CProtect 5 device. If you have a very long distance, over 100 km, you will use the optical repeater on both sides. On the CProtect 4 device, you will have such a repeater, and on the CProtect 5 device, you have the fiber optic repeater. Or for the pilot wire communication, you will use the communication converters. Only in case you have a retrofit application where you replace a CProtect 4 device with a CProtect 5 device, and here you have using the FO17, FO18 or FO19 long distance fiber optic modules, you cannot directly connect the CProtect 5 device to the CProtect 4 device, because the framing of the FO17, 18 and 19 module is different compared to the long distance fiber optic modules on the CProtect 5 series. In this case, you have to use a fiber optic repeater for the direct connection with the CProtect 4 device, and the connection between the CProtect 5 and the fiber optic repeater will then be the 820 nanometer multimode connection. In this application, you will also set slightly higher settings for the CT errors, which increases the stabilization a bit more. In the second part of this tutorial, I will present you the differences between the both workflows, the advanced and the classic protection interface. In fact, it's just a different workflow which is introduced in the firmware version 8.60. On the left-hand side, you see the workflow for the classic protection interface in DIGSI 5, where all the settings are made in the Properties tab of the communication module. For the advanced protection interface workflow, now we have a dedicated new function group in the object-oriented structure of DIGSI 5. So the settings are made within the new function group protection communication. The new workflow for the advanced protection interface is available for the Ethernet BD module, particularly used for line differential over IP networks, and also for all the USART modules. Both workflows can be used within the same device for different protection interface modules. There is also a compatibility between the differential protection communication between the devices using the old and the new workflow. The new workflow also supports the remote devices running with an older firmware version than 8.60. You will also have the full CProtect 4 compatibility is full provided. And for the multi-ended line protection, there are some changes. For the old workflow, the multi-ended line differential protection was controlled using the significant feature, which was an order option of the device. With the new advanced protection interface workflow, you will use the function point manager, or you will use function points to enable a multi-ended line differential protection. If you have a device which already has such a significant feature and you don't want to spend additional money for the function points, there is also recently available option in the function point manager which supports the conversion of downgrading the significant feature to an equivalent number of function points. So you see the advanced protection interface brings some benefits. It's more flexible in the functional scope of the device. You also have the possibility to use a line differential over IP. There are some special applications for a multiplexed operation of the protection interface, which Nina will show you later. There's also some other special applications where you want to have a phase rotation in the communication channel between the devices. So this is supported only by the advanced protection interface and not with the classic protection interface workflow. And up to 3 function group lines can be within one device. Each of these function group lines will have then a line differential protection. So this is also only available with the advanced protection interface. Here you will see one example for this multiplexed operation of the protection interface. Consider you have a hybrid line. A hybrid line is a mix between an overhead line and some cable sections. Here I have some example from a transmission system operator in Germany from Amprion. In this particular example, you have a section of overhead line which comes to such cable transition station, CTS, where you will go to underground cables. Due to the loading of the overhead line of 4000 amps nominal current, you need 2 sets of cables to transmit the power. And here we have an application example for using this multiplexing of the protection interface. Forget about the overall protection of the line between the stations A and B and just have a look at the cable sections, where we also want to use the line differential protection to protect the cables. You will need the communication channels between these cables, but if you build such transmission cable trench, you have the possibility to lay this communication also in that to the systems. So the multiplexed operation of a single protection interface is shown in the slide here. This is the same figure. So we just have a look at the line differential protection devices, and the idea of this multiplexing is to just use one single protection interface and using the communication data to transmit over a single path. So here the bandwidth of 2 megabit is required. So this is only available for direct fiber optic connections or for Ethernet-based line differential protection. As I already said, the new advanced protection interface provides that you protect more than one function group line. In this example, this is still one line which is protected, but you have 2 cables. So one device in this example will protect both cables and using one protection interface. In case you say this is not good because the communication channel will fail, you have the possibility to use a redundant protection interface, and you can also use a multiplexed for this redundant protection interface. So each of the devices will now have 2 protection interfaces, protection interface 1 and 2, and both of these protection interfaces will get the data from both function group lines and for both line differential protection functions to transmit to the remote inside. So here you have a redundant multiplexed operation of 2 protection interfaces. As you see, this is kind of a special application, so not the normal case, but we wanted to show you such an example why we introduced such a feature. Here you see a decision matrix. Should I use the advanced protection interface or shall I use the classic protection interface workflow? If you have a user module, in general you have both options. You can use the classic protection interface or the advanced protection interface. But if the number of devices should be extendable, or you have special applications for the protection interface, like I showed you, the multiplexed operation or the phase rotation, or then you want to protect more than one function group line, then you have to use the advanced protection interface workflow. Also, if you are using the Ethernet-based line differential protection, then you have to use advanced protection interface workflow only. That's enough of the theory. Let's have a look at the configuration DIGSI 5. Nina, the stage is yours.
Thank you, Philip. So now we come to the next part of the session, the advanced protection interface, a DIGSI 5 demo. And for this, I have prepared 3 examples that I want to show you now. The first example is a 2-end protection with a redundant communication. So here we have 2 redundant communication lines between the 2 devices. And the functional architecture behind this looks like this. So we have a function group line where my main protection function, the 87LDIF protection, is running. And the function group line actually represents the physical line. We have a function group protection communication, and therefore we have 2 function blocks, protection interface 1 and protection interface 2, representing the 2 independent communication channels. Furthermore, we have a function block device combination where we define the topology, the addresses of the devices and so on. In our devices, we have communication modules with 2 channels, channel 1 and channel 2. And therefore we need to configure the connection between the protection interfaces and the channels of the module. So let me show you this in DIGSI 5. For this demo part of the session, I already prepared a DIGSI 5 project in DIGSI 9.60 in this case. I already prepared for each example a subfolder and a device in it. And for the devices, I used the line differential protection template. So we already have a function group line with the main protection function, the line differential protection function running in it. Some over protection functionalities. We have the circuit breaker with, in this example, circuit breaker failure application and an auto reclosing function. But this doesn't really matter since we will fully focus on how to configure the advanced protection communication. And this is what we want to do now. So as a first step, I go to the library and look for my function group protection communication. So therefore, I have to navigate to my line protection devices, here to my 7ST87. And here write the first folder called Advanced Protection Communication. There are 2 options. Protection Communication Type 1. This is for all line differential protection applications. And Protection Communication Type 2. This is for distance protection applications. So in our case, I use the Type 1 and insert it simply by drag and drop it to the settings of the device. Within the function group protection communication, we need 2 protection interfaces representing the 2 communications channels that we have in this example. And the second protection interface can also be found in the Advanced Protection Communication folder in the subfolder Second Protection Interface. Here it is, and we insert it simply by drag and drop to the function group Protection Communication. Okay, next step I want to do is to go to the module settings. So I go to Hardware and Protocols and double click on the module. In this example, I chose a USAT AE2FO module. So this is a module either for short distances or can be used for a connection to a repeater or converter. And yeah, we have to have two channels and need to configure both of them. So I go to Protocols, here are my two channels, and I select for both the Advanced Protection Interface. So if you're more familiar to the classic protection interface, this is the classic one. It's still available. And yeah, maybe if you are used to that one, you remember that we do all the settings and so on in this properties tab of the module. And this really changed a lot when using the new workflow. Here we are more integrated in this DIGSI 5 modular concept where we work with function groups and so on. Okay, so I select the Advanced Protection Interface for both channels. The settings that are available for this Advanced Protection Communication in the module properties are quite less. So we only have the setting here, connection via, where you define, do you have a direct fiber optic connection or do you have a connection to a repeater, for example? And the second setting is for, do I want to use that module in multiplex operation, yes or no? What is meant with multiplex operation, I will explain in example number 2. So for example 1, I leave everything as the default values. Okay. Then I open the settings of my function block protection interface. And here I can do the assignment of the protection interface to the physical channels of the module. So I assign protection interface 1 to channel 1 of my module and protection interface 2 to my channel 2 of my module. Okay. In this functional architecture on the slides before, we saw that we also need a connection between the function group line and the function group protection communication. So if you want to double check this or adapt this, you found this in the function group connections and here in the tab protection function group to protection function group. In this example, it's pretty simple since we only have one function group line and one function group protection communication. The assignment is quite clear and is also done automatically by DIGSI. Okay, so here we configure the assignment function group line to function group protection communication, and in the protection interfaces we define the assignment of these interfaces to the channels of the module. The settings that you see here, they should be already familiar to you when you are used to the classic protection interface. Same is also here for device combination. So here you simply set the address of the devices and you define which one is my local device, device number 1, 2, or even higher numbers. And here you also find the parameter for the connection mode to, if you are in the connection mode CPROTEC 5 or in the CPROTEC 4, CPROTEC 5 compatibility mode. So this can be defined here. If you are interested in the CPROTEC 4, CPROTEC 5 compatibility mode, here we also have a tutorial about it. Our example, I leave it to CPROTEC 5. Maybe new for you is here the parameter IP address. this is only relevant when you are working with this line diff over IP. Line diff over IP will be explained in theory by Philip later, and in the demo by me also later in the session. If you have USART modules and not working with diff over IP, you simply use the entry 0, 0, 0, 0 as the default values are. All right, and this is already the first example. Maybe we can do a last thing, do a consistency check here. And for this device, everything looks good. And then I think we can jump to the slides and I will show you the second example. So now we are getting a little bit more complex, of course. Here the idea is that we have a double line or parallel line where we have two lines and two devices to protect it. So we need two function group lines later on in our functional architecture. To have at least a redundancy in communication, we have two modules in each device, and both modules are used redundantly. So both modules are used to connected to my function group 1, and both modules are connected to my function group 2. So here we have a redundancy in combination, in the communication at least. But of course, if one of those two devices gets broken, is something wrong with one of the two devices, you will lose the protection of your whole parallel line. So this would be a rather risky setup, what I'm showing here. At least we would recommend you to double the devices to have a redundancy also for the protection itself. But yeah, for this example, I just want to show you what DIGSI and the advanced protection interface is capable of. The functional architecture behind looks like this. So for each of the two parallel lines, we have one function group line, and of course also one function line differential protection running in it. We have also two function groups protection communication, and within each of those protection communications, we have again two interfaces, like on the example before. And we assign interface 1 to the channel 1 of communication module 1, and interface 2 to the channel 1 of communication module 2. And in the very same way, we do it for our second function group, protection communication. So here also, we have two protection interfaces, 1 and 2, to achieve this redundancy in communication. And we will assign interface 1 to module 1, interface 2 to module 2. All right, so let me show you this in DIGSI. Here I also prepared a device, a 7ST87. Let me just close all windows real quick that we don't get mixed up. Okay, so the hardware is a little different since we now need two CT inputs for the measurement of the two parallel lines. I also already prepared the function group for the two lines, so line 1, line 2 in this case, and two function group circuit breaker in this case, one for each line. So my next step will be to again insert this function group protection communication, but twice this time. So I go to the library, to our 7ST87, to the folder Advanced Protection Communication, and we need to type 1 2 times. Okay, in each of those function groups, I need a second protection interface. So this I insert also by drag and drop. Here it can make sense to give them all, not just call everything 1 and 2, but give them meaningful names. So you can simply rename everything if you have like specific names for the line connection. Okay. So now the tab function group connection gets more interesting compared to the last example. So let's start with this. So I go to function group connections, here to protection function group, protection function groups. And now we have here 2 function group lines and 2 of those protection communication function groups. Per default, they are assigned like this. Makes not really much sense. So in our example, I will assign function group line 1 to protection communication 1 and function group line 2 to protection communication number 2. So it should look like this then. And yeah, for such applications, you need here these little matrix. Then I go to the settings of the protection interface number 1, and let me jump one step back. I go to the hardware and protocols, and here to the settings of the modules. Open the settings of the first module, and here I select the advanced protection interface. As settings for this advanced protection interface, for the first module, I select multiplex operation yes. And this is where we need this parameter here, this quite new feature. Because here we need both modules for transmitting the information of both lines. So I hope it gets clear. So we will assign both protection interfaces for both function groups line to this very same channel. So we have twice the information, and that's meant with this multiplex operation. And we do the same for the second module. So also here I select the advanced protection interface and switch this multiplex operation to yes. And then I go to the settings of the protection communication, and here I start with protection communication 1 and protection interface 1. In the PI assignment, I choose the channel 1 of module in port E. And for the second protection interface, I choose the channel 1 of protection module in port F. And the very same I do for my second protection interface. So here also protection interface 1 is connected to my first module. Protection interface 2 is connected to my second module. Okay. And interesting, so here also the device combination. At the moment, the default value is always 101 and 102 as addresses for the 2 devices. In this case, in this multiplex operation, it is not allowed to that those devices have the same addresses, because then, the communication will get mixed up. So here we change the addresses to 103 and 104 for the second protection interface. And that's already it for the second example. Let's do a consistency check, and it looks good. So here we have like everything doubled. We have 2 function group lines, 2 function group protection interfaces. Each function group line is connected to 1 function group protection communication, and within this protection communication we have a redundancy. That means we use in both cases both modules, and that's meant with this multiplexer operation. All right, so that's all about example 2. Now I want to show you example number 3 in the slides. The third example is a 4-end protection in a ring topology. So this is set up, like it's shown on the slides, 4 devices, and they are forming like a ring topology. The functional architecture behind it is quite simple. So it should remind you of example number 2. We have one function group line with the main protection function in it. We have one function group protection communication. We need 2 protection interfaces because each of these devices is like talking to 2 other devices. So it's connected to 2 other devices. That's why we need here 2 protection interfaces. We have also, of course, the function block device combination, but this time we not only have 2 devices, we have a device combination of 4 devices. For the communication modules, we have again 2 channels, and each of these channels is connected to one protection interface, but here not to achieve redundancy, but to achieve this ring topology, where one device is always connected to 2 other devices. Okay, and then I would go back to DIGSI and demonstrate this to you, please. So here is our subfolder example 3. Again, a 7SD87. And I close the windows. And we start with the same setup. First step is insert the protection communication. Maybe didn't get it right. Okay, now here it is. And we need a second protection interface that I insert also in this function group. Then I go to hardware and protocols, change the module selection here to advanced protection communication. And the settings of those are totally fine with the default values here. Then I connect protection interface 1 to channel 1, protection interface 2 to channel 2. So nothing new here compared to the second example. More interesting maybe is the function block device combination, because here you define how many devices do you have in your topology, and what are the addresses of the devices, and what is your local device. Per default, we only see 2 devices. For our example, we need 4 devices. So I use the button here, Add New Stage, to insert 2 more stages, 2 more devices. And of course here, you need to give addresses to them and define which one is my local one. Maybe interesting also for you is the question, okay, what is the pricing? So I extended now my 7SD87 from a 2-end topology to a 4-end topology. And with this advanced protection communication, we changed the way in pricing this functionality. And this I want to show you here in the tab Device Information, and here in the tab Function Points. So here you always get an overview, okay, how many function points are used or are needed for this configuration. And we see here for device type 1 communication protection interface, we configured 4 instances because we have 4 devices, and this costs 370 function points. So the protection communication between 2 devices is like always included in the functional scope. This does not cost extra function points, but for each device that you are adding to this topology, you need to pay additional 185 function points. So in this case, we added 2 devices. This makes 2 times 185 equal 370 function points. And yeah, so here you can always check, okay, how many function points do I need? And then can do a last consistency check, and looks good. So we are now finished with our third example. Now I'm happy to hand over back to Philip, and he will give you a presentation about our line differential protection over IP.
Thank you, Nina, for these configuration examples in DIGSI 5. The next part of our webinar will focus on new communication technology based on IP Ethernet networks. The legacy technology used for wide area communication networks is the time division multiplexing, TDM. In such networks, each participating protection device has an assigned constant bandwidth. So each device can transmit and a predefined amount of data at a specific point in time. So the technology is from a telephone network running at 64 kilobits, which is 8-bit times 8 kilohertz sampling. So the benefit is that the data is transmitted periodically and deterministically. Today's networks are typically packet-switched networks, PSN. In such networks, the data is transmitted in form of packets of different lengths and priorities. Each participating device can send packets at any time. If several packets arrive at the same time, they are stored in buffers and processed in the first-come, first-served principle. Advantages of such networks are that the bandwidth efficient data transmission. For line differential protection communication, a constant data flow is critical. Otherwise, the applied ping-pong method does not correctly measure the channel delay or estimate the device time offset. For this application, a legacy communication channel can be emulated, the so-called pseudo-wire, in MPLS networks using two common methods. One is the so-called SAT-top, which stands for Structure Agnostic Time Division Multiplexing, TDM, over packet. Here we have a transparent mode, so it's a bitwise transport of the TDM signal. And the second one is the so-called CESO-PSN, which stands for Circuit Emulation Service over Packet Switched Networks. Here the TDM signal is decoded and transmitted. Such a pseudo-wire route needs to be defined in an MPLS network using the network configuration tools. Using the quality of service flag, the time critical data transfer is realized between the label switched routers. Typically, also alternative backup routes can be defined in case of a communication path fails. Such a transition from a TDM to a packet switched networks is an ongoing process for many TSO and DSO worldwide. The line differential protection communication uses a Siemens proprietary application layer protocol, which is a hop-by-hop communication in a ring or chain topology. For the serial communication, modules of the devices are connected using a direct fiber, pilot wire, or via communication converters to wide area networks. For the new IP-based line differential communication, the devices are all connected to the same IP network. What are the requirements for the new IP-based line differential protection? At the moment, only the modular devices of CPROTEC 5 support this feature using the Ethernet BD2FO module. The firmware version 860 is required, and also the configuration is made using the new advanced protection interface workflow as presented before. A new UDP IP4 communication protocol was implemented on the BD module to support this feature. It also supports the IEEE 1588 time precision protocol running on the same module. Please note that the IP-based line differential protection needs an external time synchronization. So this can be done using IEEE 1580A, PTP, or a 1 pulse per second. The line differential over IP can also be used in mixed applications using the older CPROTEC 4 devices, as shown here in this example. The CPROTEC 4 to CPROTEC 5 communication using a traditional communication path, and the CPROTEC 5 using the new IP-based line differential protection. On the physical layer, this is expressed on the top of this slide here. So this is a traditional path, and this is a new IP-based path. On the logical level, you see that the CPROTEC 4 devices using a protection interface 1, using the index 1. The remote end relay is the device with the ID 102, index 2. And in between the CPROTEC 5 devices, we have this IP-based communication channel. Also, very complex mixed topology of serial communication paths and IP-based communication paths can be realized as long as a chain structure is possible between the devices, which is marked with this yellow line. Please note that the external synchronization in such an arrangement is only required for the devices using the IP-based line differential protection. I will now hand over to Nina again. She will present you the configuration steps for line differential over IP in our setting tool DIGSI 5. Nina, please.
Okay, yeah, thank you, Philip. Now we come to the last part of our session, the line diff over IP DIGSI 5 demo. So in this demo, I want to show you a simple example for a two-end protection for a diff over IP scheme. It means we have here one line, two devices to protect this line, and one communication link between the two devices. In this setup, we have one protection function group line with the main protection function line differential protection running in it, and one function group protection communication with one protection interface, and of course, again, this block device combination. Maybe new compared to the examples before earlier in this session is that we need here the block external synchronization. In the communication modules itself, we will only use one channel. This channel will be connected to the protection interface 1. So much of the background of this example. Now let me show you this in DIGSI. So now we are in example 4. I have a 7SD87 already created. And under hardware and protocols, you see now I have inserted an Ethernet BD module. This Ethernet BD module is mandatory when you're doing diff over IP configuration. Okay, but we will start in this similar way as for all the other examples earlier in the session. I will start by inserting my function group protection communication. So I go to the library and here in the folder advanced protection communication and insert protection communication type 1 to the device settings. Here, so we already have one protection interface and one function block device combination. This is sufficient for this example, but what we need now is one function block external synchronization. So this I also add via drag and drop to this function group protection communication. Okay, next step is I go to hardware and protocols and take a look at the settings of my Ethernet BD module. So here under protocols, of course there are now a lot of options, but when you scroll down, under the headline Others, you find the Advanced Protection interface, and you activate this by activating this checkbox. Yeah, DIGSI needs some seconds. And yeah, so we see now the checkbox is activated, Advanced Protection interface is active. The settings are, yeah, not relevant. Here you can simply leave the default value as it is. Here under the settings or the protocol selection of Ethernet, of the Ethernet BD modules, I will also activate the IEEE 1588 time synchronization. So as Philip explained in his part about line differential over IP, we need here always external time synchronization. And yeah, this time information must be received somehow from the device. There are different options. In this example, I want to demonstrate how to use the Ethernet BD module for receiving this time information. Okay. So I scroll down, and here under Network, you see the IEEE 1588, and this I will also activate. So here the idea is now we use our Ethernet BD module in port E to receive the clock information from the external Grandmaster clock. So let's go to the settings of the protection communication. I start with the protection interface. And for the PE assignment, I select the Ethernet BD module. As synchronization, here is already selected that we need an external synchronization. And already this function block external synchronization 1 is assigned to my protection interface 1 per default. So let's take maybe a look at this external synchronization. So here's just the name of it, and more interesting, the synchronization source. So here you have different options. In my example, I wanted to show you how to use this Ethernet BD module as time source. And so I select as synchronization source here our Ethernet BD module. And here also, per default, it selects the IEEE 1588, since this is what I configured for the Ethernet BD module. And let's take a look at the device combination. Here, under General, the settings are more or less equal to the classic protection interface. Quite new or specific for the line diff over IP is the setting of the IP address, because this is very important for that the devices are able to communicate with each other, that they know the IP addresses of the other devices. And you see here, at the moment, my local device is defined as device number 1. And for device number 2, there's also already an IP address set. And it is also grayed out, so it cannot be changed here. And this IP address that you see here is the IP address of your Ethernet BD module. So when we go back to hardware and protocols, and here to the settings of the Ethernet BD module, you see here under IP interfaces, you can define an IP address of this module. At the moment, this is these 10, 16, 60, and 60. If you change it here, it will be automatically changed in the device combination. Okay, so I jump back to device combination. Here we see the IP address of the local Ethernet BD module. Of course, for all the other devices in the topology, you must enter it manually. And of course, it should not be the same, so I simply set it to 10, 16, 60, and 61. but this of course must fit to the real setting in your other device. And yeah, that's already all the steps you need to do to configure a line diff over IP system. So let me do a consistency check. If I missed something. No, it looks good. And then, yeah, you made it to the end. We are at the end of this session. I hope you enjoyed it. Thank you for your attention, and I would be happy to welcome you in one of our other sessions. Have a nice day.